Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will continue our discussion about simple linear regression. To be more specific, we are going to find an alternative form for the least squares regression line by solving the normal equations. And then we're going to establish a relationship between this alternative form for the least squares regression line and the original one, the old one that we talked about in another video. Okay? So let's begin. So let me remind you what we did in another video. In another video, what we said is that we were going to be finding, right, the best line, the one that fits our data best in terms of the sum of squares for error, the one that minimizes the sum of squares for error, using these formulas, right? And in your textbook, they use that notation A sub 0 to underline that this guy is the y-intercept when x equals 0, okay? The predictor is equal to 0. So after taking partial derivatives of the sum of square for errors, right, with respect to a and b, we ended up with these formulas. This was the formula for the slope, and this was the formula for the y-intercept. And we also mentioned that in your textbook they use this funny notation for this kind of a cross product. For instance, the summation of xi yi divided by n, x times y, the whole thing bar, right? Which is different from the product between x bar and y bar. Okay, so just be careful with that. Okay, so that's what we did last time. So now what we're going to be talking about is an alternative form of the least squares regression line. Okay, so the alternative is going to be this. Let me just write it down like a capital A and a capital B. And the difference between the original and the alternative is that here what we're going to be doing is, before we find A and B, we're going to be centering the x's with respect to x bar, their sample mean. Make sense? Okay? And then after we do that, we're going to see the relationship that we have between A, uppercase A, and lowercase a0, and between uppercase B and lowercase b, the one for the original. Okay? We'll see if they are related and how they are related. Okay? Okay, so we're going to be doing basically the same thing that we did before to find the best lowercase a sub 0 and lowercase b, right? We are going to be minimizing the sum of squares for error. So let me remind you what the sum of squares for error looks like. It's just the difference between your observations, yi's, right, and predictions. You square those differences and then you add them up for every single observation in your data set. Okay? Okay. So the criterion is minimizing this, right? So criterion, going to minimize with respect, in this case, with respect to A and B, right? Uppercase A, uppercase B. Okay, so if we rewrite that, okay, let me rewrite this, since y I hat is defined like this, let me just, substitute that here. Okay. Okay, so that's our criterion. Okay. We know what we have to do, right? We will have to take partial derivatives with respect to A and with respect to B, and we're going to have a system of linear equations. Well, yeah, a system of linear equations that we will have to solve. Okay, so let's do that. It's not going to take that long now that we know how things work. Okay, so it's going to be partial derivative of that with respect to uppercase A, so we're going to have 2 times that times the derivative with respect to uppercase A, right? And then we're going to set it equal to 0. So no problem. That's going to be our first equation. Let's do the same for B. So again, we have 2 times, the derivative of a sum of derivatives, we're going to have 2 times sum of these guys, then the derivative with respect to B, and in this case the derivative with respect to B is going to be minus xi minus x bar, right? Okay, and then we're going to be setting that equal to 0. Okay, we good? Okay, so just like we did before, we know that it's a good idea to simplify these equations before we solve them. So let's play around with the first one. So this one is the same as -2, right? We can factor that out, that -2. And then we can divide on both sides by -2, and then it would go away, right? Okay, so we have simplified that one. Let's do the same with this one here. So again, we're going to have -2 here. That's going to be a common factor. We get to pull it out. We divide on both sides by -2. It goes away. Okay? Okay. Now let's try and do some algebra with the first equation, and let's try and solve for uppercase A. Okay? So here we are. So this is going to be summation of yi's, no problem, and then we're going to have minus n times A, uppercase A, right, minus B times summation of xi's, well, summation of xi minus x bar, right? So let me place it here. We're going to have this guy. Make sense? Okay. Now, let's just quickly talk about the last term. Let's talk about this guy. Note that this is the same as the summation of xi's minus n times x bar, right? But note that this summation of xi's is the same as this. We could multiply by a1, right? If you multiply and divide by n, right, what you have here is that this guy is n times x bar, right? Summation of xi's divided by n times n, you have n times x bar minus n times x bar. So that's just 0, right? Okay. So it turns out that our equation number 1 is equivalent to this. It's just equivalent to this, right? Can you see it? Because that third term is 0. We just showed it's 0. So when you solve for a, guess what? It's really beautiful, because then you have plus n times a, right? And then you divide on both sides by n, and then you end up with, you know, just y bar. Make sense? So a is just y bar. So using this alternative form, for starters, it seems to be simpler thus far than the other one, the original, the regular one that we talked about at first. Okay, so now we have that one. Okay, so now let's talk about this guy. Let's do a little bit of algebra, just like we did for the first equation. And remember, the set of these two equations, it's called the normal equations. Okay, so same story here, right? Let's try and do a little bit of algebra with these guys and see what happens. Okay, so in this case we're going to have summation of yi times xi minus x bar. So we're going to have that here. Then we're going to have minus a times xi minus x bar, right? Okay, and then we're going to have again, we're going to have a minus that affects that guy, the last term, right? That minus affects both a and b times xi minus x bar, right? So, and this one here is going to be squared. Okay, there we are. Yeah, it looks good. Yeah. Okay, so now we don't need this guy anymore. Correct? Okay, now let's expand. Let's this is the same, right, as the sum of yi's minus xi minus x bar, right? Then a is a common factor, and we are going to have the sum of the xi's minus x bar, right? Okay. Then again, b is a common factor. pull it out. Oops, not what I wanted. I need a summation here. So as I was saying, b is a common factor. We can pull it out, and then we have this guy here, right? Okay, right? No problem. So we have summation of these three terms is the same as these three sums, right? But now, recall what we did earlier. We showed that the summation of xi minus x bar is 0. Then that means that this guy here in the middle is just 0, right? So now what we have is this. Okay? And then we can easily solve for b from that expression, right? So solving for b, let's see what we end up with b. This guy would be here on the right hand side, and then we would have summation of yi's times xi minus x bar, right? And then we divide that by summation of xi minus x bar squared, right? And let me just write it down like this. I like this way better. Yi. Okay? Make sense? So note that we have very quickly found the best A and the best B. The best A is going to be y bar. The best B is going to be just this guy, summation of xi minus x bar times yi divided by xi minus x bar squared, right? Okay, now we had the old one, right? This is the alternative form of the least squares line, and we had the old one, right? And for this one, this is what we have for the slope, and this is what we have for the y-intercept. Okay? So what I claim is that lowercase b and b are the same. Okay? So let's try and show that the slopes are the same for both the original and the alternative form for the least squares regression line. Okay? So here we go. Let's open a new one. We claim that lowercase b and b are the same. So let's prove that. Let's prove that's the case. The proof would be something like this. So this is what we got before, right? Okay, so let me borrow that for a sec. We got that from the other video, right? But it's a given. Right? So we know that lowercase b is given by that expression. Okay? Now, these guys cancel out, right? Okay. So, I could divide by n minus 1. I mean, these n's cancel out, right? we just divided by those n's, so you could end up with the same expressions that you see in your textbook, right? But what we had at first was just this guy and this guy, right? So just as we divided by n here and here, we could have divided by n minus 1 instead. Okay? So the thing is, if you do that, when you see this, right, what you should recall is that, hey, this guy is the very definition of the sample covariance. Remember? Okay, so this would be the sample covariance. Let me write it down with that notation. And when you see something like this, you should go, oh, that's the alternative expression for the variance of, you know, x. Make sense? Okay. Okay. Now, another thing that you should note, right, is that the definition of the sample covariance is this. The summation of xi's minus x bar times yi minus y bar, right, divided by n minus 1. That's just the definition. Okay? The one that you had here is the alternative formula. And we can do something similar for the definition of the variance, right? We know that the sample variance of x is just this guy. Okay? Now those guys cancel out. The n minus 1s, those guys cancel out, right? So what we could have is just this, and this. Okay? Make sense? Okay, now, and this is lowercase b. Okay? Let me just make an additional observation about the numerator. Let's play around with this guy. Just this guy, that's the one I am interested in. So this is the same as the summation of xi's times yi minus, and then we're going to have this. Oops. Oh, come on. So I have that. That's the first one. That's the second one, right? That sum is the same as that sum. Okay? Now, this guy here is a common factor, right? So I get to pull it out. But remember that we showed when we derived the estimators for the alternative form for the least squares that the sum of xi's minus x bar is 0. Remember that we did that? Right? So let me go back to what we have here. So this one here is 0, right? So this is the same as this. Just this. Oh, come on. Let me copy paste this and kill the last one. So this one, oh, this one is 0, right? So we only have summation of xi's, right? Xi minus x bar times yi. Make sense? Because this guy is 0, right? Okay, so now let me plug it in here. So we have this, but the truth is that the only one that matters is this guy, right? That's what we showed here. That summation of xi minus x bar, yi minus y bar happens to be the same as this. Because this guy here, summation of xi minus x bar, is 0, right? But guess what? If you go back to where we derived b, uppercase B is summation of xi minus x bar yi divided by summation of xi minus x bar squared. Right? That's this guy here. So we're done. We have shown that, yeah, lowercase b, meaning the estimator for the slope for the original form of the least squares regression line is the same as the slope for the alternative form for the least squares regression line. Okay? So b for this one and uppercase B for this one are the same. The slopes are the same. Okay? Now, something more. Let's rewrite the original. Okay? So let's go back to the original, just so I can show you something. So from your work, we know that the one for the original, right, the estimator for A0 is going to be y bar minus b times x bar, right? That's a one for the original. That's the estimator for the y-intercept for the original. Plus b. Let me just leave that guy like that. b times xi. Okay? Now, let's do a little bit of algebra. So this is the same as y bar. Let me factor out that b, and then that's the same as b times x bar minus xi. But guess what? What we have shown is that, remember that we showed that for the alternative, uppercase A was y bar, and we have shown that lowercase b and b are the same. So guess what? This is the same as uppercase A, right? Oh, and then this should be, it would be better if we factor out, instead of negative b, let me factor out b, right? Because in that case I'm going to have this exactly the way I want it. Okay? If we factor out b, right, would be b times xi minus b times x bar, right? So, as I was saying, that a, right, that y bar is the same as uppercase A, right, meaning the one that we showed for the alternative. And we have already shown that lowercase b and b are the same. Okay? What it means is that your predictions will be the same using the original or the alternative. Okay? Which makes sense, right? The only thing is that you're using a different point here. You know that you could define a line like this, right? All you need is the slope and one point, and that point could be, for instance, in this case, the y-intercept, or it could be a different point. In this case, what you have is that the least squares regression line passes through x bar and y bar. Okay, so just using a different point to define the line, but it's the same line, which makes sense because you're using the same data set to estimate that line. So your estimations will be the same. Make sense? Okay. Now, let me just make a final comment about that alternative form that we found. Okay? So, it turns out that it's going to be more convenient from a Bayesian perspective to use that alternative form for the least squares regression line. You'll see it. Okay? So, we're going to be using this one instead of the original one. Okay, with a y-intercept, meaning where the point, with the point where the line crosses the vertical axis at 0. Okay, so we're going to be using this one instead, the alternative formula, because for from a Bayesian perspective, it's going to be more convenient. You'll see for calculations it's going to be better. But as we have already shown, right, our predictions will be the same using the original or the alternative, which, you know, makes sense. Well, that's it for now, guys. Thanks for watching. See you next time. Take care. Bye.